First talk of the event is by Professor Shankar Kumar Selvaraja on Photonic Integrated Circuits and how they can be used as platform for quantum computing. Professor Shankar is an associate professor at the Center for Nano Science and Engineering at the Indian Institute of Science, Bangalore. He is the chair of National Nano Fabrication Center at IISc. He has joined IISc in 2014, and before that he was working at IIMec, Belgium, where he also received his PhD for his work on wafer-scale fabrication technology for silicon photonic integrated circuits. He's an alma mater of Bharathiar University, College of Engineering, Guindy, and University of Twente, the Netherlands. He has published over 250 research articles in international journals and conferences and has 8 patents. And his current area of research includes silicon photonic IC, enabled connectivity, computing, sensors, and quantum photonic integrated circuits. So the talk will be followed by a small Q&A session, and I would like to request everyone to put your phones on silent. So we warmly welcome Professor Shankar Selvaraja to impart us knowledge on the photonic integrated circuits.
All right, good morning. Can you all hear me? At the back? Good? All right. So first of all, welcome to this second edition of workshop on quantum technologies, Q-Karyashala, and I presume that the cross-section of audience here is reasonably broad. How many of you have had any courses on quantum? Okay, the majority is still common. All right, great. So I've kept this talk to be reasonably broad and at a higher level, all right, so that different cross-section gets, different feed on the status of things today and also why we want to do this, right? As Arindam mentioned, right, so quantum has quite a broad application space. Computing is a section of it. Then we find its application, in sensing, right, quite actually much more, right, than what we can think about today, right. So what I'm going to do today is give you a feel for quantum computing, right, but using photonics, all right. So before going there, we work here at IISc. There's a very large photonic computing initiative here at IISc. Arindam is also part of it, along with Joydeep, Basu, and also Kaushik, along with few other faculty members. All right, this is the team that does most of the work, right? And thanks to the team, right? We have both, project staff, PhD student, postdocs, and research staff contributing to the work that we do, right? And they're excellent folks coming across the cross-section that is sitting here, all right? Firstly, let's look at photonic integrated circuit. So probably some of you might not heard of this word, right? Photonics, of course, we know. Integrated circuits, of course, we know. But then putting it together, why, right? But let's start with integrated circuits, right? Or rather, chips, as we know, right? There is quite a lot of buzz around national semiconductor missions where we want to make chips, right? Semiconductor chips. Let's start with some rationale, right? So why we want to make these chips, right? Basically, this is good enough, right? Where you make PCBs with discrete components, right? I use resistors, capacitors, inductors, and microprocessing elements, clock generators, or rather crystals to generate clocks and so on. I can realize functionality on a board, right? But it's not scalable, as we know, right? It's a real estate problem and also functionality problem. So what we want to do is we want to realize these bulk processes, what we call on the PCB or a large, form factor, onto a flat, thin substrate, right? This substrate can be anything. And silicon is one, right? It can be 3-5 semiconductors like gallium arsenide, indium phosphide, or it could be some metal oxides like lithium niobate, barium titanate, strontium titanate, or it could be just dielectrics, right? For that matter, it could be quartz, oxide, right? So there are various substrates that are available, but based on the application that we are looking at, right? If you are looking at electronic applications, right, you want the substrate to be conducting, insulating, all that kind of things, right? But if you are looking at purely optical, you just want the substrate to be transparent, right? So transparent to the wavelengths that you are looking at. So that's the main idea of going from a bulk, configuration onto a chip. And then what is the advantage in doing that? Okay, it's an academic activity of miniaturizing it, everything. Do I have value in bringing it, right? So the value is in front of us, right? So we basically, all of us are carrying a computer in our pockets, right? So it's not a phone anymore. We don't call it as a mobile phone anymore, okay? So this is actually a computing element that you are carrying, right? It's as powerful as your laptop, right? And sometimes some of these configurations are more powerful than your laptop, okay? So that is the advantage of bringing these functionalities onto a single substrate. Integration brings functional enhancement and performance enhancement. So that is the main driving reason why we want to push towards everything towards chip scale, implementation, right? So when it comes to photonics, or rather, quantum photonics, why are we interested in, miniaturizing these things? This came out, about 3-4 years ago, right? The first of a kind demonstration of what we call quantum supremacy. Basically, what this did was to show, boson sampling at large scale, right? So this is a very nice experiment to show quantum computing using photons. But then this requires, a dozen of PhD students, around the table aligning the optics to get what you want, all right? So this is a very good academic activity to show the potential of photons that can be used for quantum applications, right? So in this particular case, computing. But then this is not scalable, we know that. Some of you are from industry, you will see that, okay, it's a very nice picture, shows very complex. Congrats to the PhD students who got this thing done and wrote a paper about it, and there ends the enthusiasm, right? So that's not what we are looking for. We want to push this to something that is scalable, right? And put it on a chip, right? Chip so small that you have to actually mark it and say, can I put it into a small chip which is maybe about 5 millimeter by 2 millimeter or 5 millimeter by 5 millimeter, right? What you see there is about 5 millimeter by 2 millimeter chip. Is it possible to do that, right? What we need in order to transfer this whole, 8 feet by 8 feet table onto a 5 millimeter by 2 millimeter chip. How do we do that? What are all the criteria? What are all the constraints that we have? Is what we will, discuss in the next 30 minutes or so. Before going into that, I want to start with why quantum and why quantum computing is something that's going to be disruptive. All right. So starting with this classical bits, this is something all of you know, right? All the computing that we do today is based on bits, right? All the analog signals that we generate today are converted to digital, and then the processing happens in the digital domain, right? So we manipulate all the data processing in here. And also there is a different school of thought that is emerging, just neuromorphic computing, where computing is analog, can be much more power efficient than digital, right? That's a different argument, and that's a different presentation for another day. But this is the majority of the computing that we do today, which is limited to 2 bits. But then if you look at qubits, which are quantum bits, they are much more strong, right? It's not zeros and ones. So I just take the 0 and 1, which is in a one-dimensional representation, through a three-dimensional representation. I take a sphere, and every point in this sphere is a potential bit. All right? And that gives you infinite possibilities, right? And that is the power of quantum, right? I'm not just going to use zeros and ones to define my data. I'm going to use this qubit that can define, infinite number of positions, right? And we can make it even more disruptive, what we call entanglement. I can take these two qubits and mirror that. These two qubits are twins, right? So they share all the properties between each other, and I can define states between these two. So now my potential for, state, or rather, the bits that I can define now increase to even higher, right? So this is the evolution of why quantum computing is disruptive, right? Just to make an argument that, you need to have different states, or rather levels, to define your problem or your data that you have. So now let's look at some analogy between, the regular bits and the qubits that we have. If I have 10 qubits, right, it can define about 2 to the power of 10 values. All right. So that is the power of the qubits that you can give, because each one is going to be in a different state, and I can define it. And if you map it to the regular, digital bits, right, it's about 16,000 bits. Right. You can already see the effect, right? I'm only defining 10, all right? So now it has scaled to 16,000 bits now. Right. Now if I go for entanglement, right, let's say I'm pushing here really hard, if I take it to 500 entangled bits, and actually we don't have enough number of particles to even define those in the classical sense. So that is the power of quantum. So this definition is helping us to store data or define states with which I can do processing. All right? So this is the power of quantum altogether. Right? So what we try to do in computing, particularly quantum computing, is to increase the number of bits that we can generate, and also create entanglement, which is a large number of bits, so that I can, access a huge working space for me to do this calculation, right? So your calculation is limited by the space that you can get access to, that we all know, right? If you want to increase that space, you have to increase the memory. What it essentially means is I need to have that much possible, definition, right, in the hardware space to do that, all right? This is all good. Right? It's again an academic activity that I say, all right, if I can get 10 qubits, this is great, and if I have 400, 500 qubits, I can define anything that I want. But the question is, for what? What are you going to do with it, right? So there should be a purpose. We say computing, right? What sort of computing is the question? Am I going to use this quantum computer to do, mathematics like the regular logic mathematics? That's not going to be the case, all right? It's a very inefficient use of the power of quantum computing, right? So we are not going to use this for conventional logic computing. When I say conventional logic computing, let's say 1 plus 1 is 2, right? Which is not, trivial. And you can actually run it and show that 1 plus 1 is 2, all right? But then, are we excited about doing it? Not really. We want to solve problems that today's computing can't do. Both digital and also analog computers can't do. And what sort of problems? So you want to do a harder problems, right? And those hard problems are wild and wide, I would say, right? For example, finding human safe fertilizers. The moment you say fertilizer, it's bad, right? It's chemicals, and we are suffering from all the bad chemicals that we have been using in agriculture for years. And now there is a point that, okay, this is not sustainable. We need to find new alternatives. How do you do that? I mean, old school way of going into a lab and then doing all kind of permutation and combination is going to take forever because the problems are complex. Is there an easy way to model these compositions and then get a better idea? That's possible. But then the problem is, it is harder because there are large number of combinations that is possible, and those problems will take forever to converge, may not converge with the current resource that we have, and that is where we look for more potent, strong computing platforms like quantum computing. And then the other application is for more sort of optimization problems, right? So drive your system towards correct answer, right? But then what is the correct answer? We know the correct answer most of the time for optimization, right? If I want to reach, let's say from here to, I don't know, somewhere south of the city, let's say JP Nagar, okay? And it's easy for me to ask Google, okay, find me the route. It's actually running an algorithm, right? Taking different parameters into account, right? Like traffic, right? Which one is faster? There are other roads also, but then you want to take your cycle or you want to take your car, right? So there are different possibilities, or in bus. So all these are input parameters, and it is optimizing the way. Similarly, this human safe fertilizers is also a known, answer. So answer we know. If you ask a chemist, they will say, these are all the things I don't want in my composition, all right? But I can have it as the starting composition, but it get decomposed into something that is safe. We know the answer, but how do you drive it towards that, right? So those kind of problems find application in this quantum computing, all right? So there are different technology platforms that are available to do this computing, all right? So like you have silicon processors that does all the computing because we don't know anything else, right? That does the computing well. There are multiple platforms today we have that can do computing, right? You can start from superconducting circuits, which is something that is much more mature than photonics today, all right? Semiconductor based circuits, silicon is also playing a good role there. Ion traps, you can trap the ion and then do computing. Photonics, photons are essentially a quantum particle, right? Even from the classical sense, from day one, or not really day one, from day one it is called a particle, but then we also understood that it's also a wave, right? So photons are much more different from rest of the group here, where they are the fundamental energy that we use for manipulation, while the others are actually technologies, right? Defect sites, chemical defects can be used to do computing. Topological structures, which are macro scale structures, and then you can also use nuclear resonances in the material to do computing as well. And actually, the whole computing started with NMR. In the late or early 90s, Professor Anil Kumar here in IISc physics demonstrated quantum computers operation here at IISc, right? Dating decades before anyone came up with this technology. All right. So today we are going to look at photonics and how we can utilize photonics for doing quantum computing, or rather what we can do with it. And this is again, not academic activity anymore. Okay. So this is to show you that quantum computing is not something that we do only in the lab, right, where PhDs are generating know-hows and so on. We have a complete ecosystem already built now, right? From hardware, to technology builders, to actually end users. You can look at the end users. I mean, you can recognize and relate why they are using it. For example, Merck, right? Merck is a very large chemical company. Airbus, for example, is an aerospace company. And you're asking why Airbus is using or interested in quantum computing, because the problem is very complex, right? You're looking at large-scale interaction, right? JP Morgan is using it, okay? Wells Fargo is using it. They are finance companies. Why are they interested in quantum computing? Because the nature of decision for any investment or any change in the financial market depends on large number of micro effects, right? A small microfinance failing in a village can result in a huge effect at the larger macro scale in the country or even in the world. How do you predict that? How do you make sure that you are taking all the parameters that you want to take your decisions? All right. So there is the potential is immense, and there are enough investments that's it. And I just want to bring your attention to photonics here. So there is already large investment that has gone into Psi Quantum, Xanadu, Orca, and then Candela, and there are few others as well. So Xanadu and Psi Quantum are leaders at this point of time. I'll show you what they have done, right, in terms of photonics. And as I mentioned, silicon semiconductors are also really strong, along with ion trap, atoms, and these are all the light sources that feed into this technology. So the takeaway here is quantum computing is not just an academic topic, okay? So it's actually a technology that's coming out. All right, so let's get into the photonics part. So now we have enough background, and we are all convinced that quantum computing is the technology of the future, and photonics is going to play one of the key role in realizing this computing platform, right? So what do you need in order to realize this platform? What are all the toolboxes that I need to make a quantum computer, right? So there are different functionalities. Photonics, if you take a photon, you want to manipulate the photon, right? So you want to generate the photon, you want to couple the photon in and out, you want to guide where you want the photon to go, and the photon has this very interesting property of wavelength, right? So it has a very distinctive property of frequency or wavelength, and we can distinguish between different photons. And that's the main reason we all like photon, because that's what you want for quantum technology. You don't want this particle to interact with any other particle to lose its state, okay? So bosons are very good, and that's why we love photons for that. And modulate or change the phase of, or rather the state of the photon, that's what we call modulation here, and then detect the photon. So these are all the basic functionalities that we want in order to realize this functionality, all right? And these are all some of the images, scanning electron microscope image and optical images of what we have made here. So this is something to reiterate, that photonic integration brings you functionality integration. I'm talking about hundreds of functionalities, device that I was showing you, right? Waveguides, filters, detectors, you can all integrate it on a single chip, right? It's not a bulk module anymore. It can be very power efficient, because I'm not putting bunch of lenses along 8 feet table anymore. It can operate at very high speeds. Not just because the light is fast, but I can change the state of the light very quickly, all right? Which gives you high speed that leads you to large bandwidth. Can be very compact, lightweight, obviously. Low latency is very important. Latency is a big killer, when you talk about coherence and so on. So you avoid high speed or rather efficiency through this low latency. And it can operate at different wavelengths as well. So you can operate at visible wavelength, or you can also operate at near IR wavelength, whatever you want, all right? So that's a power of photonics integration. Let's just focus into what you need for a photonic quantum computer. What are all the components that we need? We saw broadly what are all the functionalities that we want in the toolbox, but this is much more focused onto what are all the functionalities we need in order to realize a simple quantum computer. One is light source. So you want a quantum emitter coupled to a waveguide. So waveguide, these lines are the ones that are going to carry your photon. It's like a metal wire that carries electron without losing the electron, but these wires are, conductors for photon. So it's going to take the photon. We don't call it as a wire, electrical wire, since it is carrying a wave, right? The analogy comes from the wave optics, so we say it's a waveguide, okay? The photons can go through this, all right? And then we can change the phase and also the route for that a particular photon takes, okay? So you can push the photon into one arm, or you can go to the other arm. This is a basic unit, which I will again come back in a later slides. So directing the light where you want depends on how you change the phase of the light, all right? And then you need to look at some kind of non-linearity, right? So non-linearities are very important aspect in quantum optics, where light generation and energy distribution becomes important, which I will also show you a little later. Confining the light for non-linearity again is important. Spectral filters, which we already saw, right? Filtering out different photon energies, right? That's what spectral filter is about. The energy is related to color, right? So spectral filters, so we need to do that. And of course, waveguide integrated photodetector. So all of this could be integrated on chip. So now, like any other microprocessor chip that you buy off the shelf, plug it in and use it, maybe in future what we envisage is that the whole circuit need to be a drop-in module. So I just apply some power and it should do quantum computing, right? So that is a long-term vision in realizing this, right? So everyone across the world is trying to get towards that, okay? And this is something that we are proposing slightly in a different module. Here at IISc, there are initiatives to generate and prepare quantum bits, and then you have interferometric and phase shifter matrix, and then you have on-chip single photon detectors, right? So let's break it down into different sections so that we understand and appreciate what are all the scopes and also work that one can do and where things are at this point of time. So I talked about waveguides, right? So some of you might not have seen or heard about this particular term, waveguides, okay? So let's just look at it what it is, right? So for all practical purpose, you have already seen this in some way or actually used this in some way, okay? For example, optical fibers. How many of you have not heard of optical fibers? That's good. So all of you have heard of optical fibers. Optical fibers are nothing but waveguides, okay? It guides light, all right? It's a silica, cylindrical structure that has a core and then it has a cladding, all right? So the light travels inside the core for kilometers without loss. What am I trying to do here? I'm just guiding the light, right, where I want, all right? So that's in a macro scale. We scale it down and put it on a chip with slightly different material system. That's all, right? The concept is making sure that you transport light without loss, okay? Or transport light wherever you want without loss or low loss, okay? And just to give you some size, right? The core of the optical fiber is about 9 to 10 micrometer. And the cladding is 125 micrometers, so it's as thin as your hair, okay? So that's optical fiber that can carry terabits of data, right? So that's the potential of light that you have. But now we are going to use the same physics to do chip scale, light guiding. So instead of circle, we are going to make it, like a rectangle or a square, right? Where we call core is where the light is going to be, and clad, it's a cover, right? It's a protection layer. So the density is what is defined here as a refractive index. Okay, refractive index is the optical constant of a material, right? If it is dense, the refractive index is high. When the material is, sparse, the refractive index is low. It also tells me something about the transmission as well. If the refractive index is complex, it is complex, but if the imaginary part is non-zero, that means it has some absorption, right? This comes from the solid state physics, understanding of where these material properties originate, okay? So in this particular case, it's all transparent, so we are not bothered about the imaginary part of the refractive index. So the refractive index of the core should be higher than the refractive index of the cladding. So this difference, what is called contrast. You want this difference to be large, and if the difference is large, you can squeeze the light inside this small space. Why? Because the wavelength of light depends on the material it is traveling, okay? So lambda naught is the free space wavelength, and lambda naught over n is the wavelength of light inside the medium, okay? So wavelength of light changes based on the medium it propagates, okay? This is very important to understand. That's why if you have this n to be very large, the wavelength will become small. If the wavelength becomes small, I can squeeze the wave inside a small space, okay? And just to give you an example, 1550 nanometer is the telecom wavelength, right, where we transport all our data. And if the refractive index of silicon is 3.45 at 1550 nanometers, right, then the wavelength of light becomes 450 nanometers. So 1550 nanometer wave is now squeezed to 450 nanometer. That will fit into my tiny waveguide that defines the size. So this waveguide, right, which is surrounded by silicon dioxide, is less than half a micrometer. So it's about 400 or 450 micrometer. Yeah.
So if I can design a 450 nanometer core, so I can effectively trap the photon.
Yes. Yes. So this photon of 450 nanometer wavelength. When you say photon of 450 nanometer, you have to be a little bit careful. It's a 450 wavelength. The frequency is different from wavelength, okay? So most of you, if you are coming from physics or engineering background, if you are from engineering background, perhaps if you have done optical communication course, you only talk about wavelength. We don't talk about frequency. Wavelength changes from material to material, but frequency remains same. The photon energy remains the same, but the wavelength changes, okay? That means the color is not changing. I'm not going from a near IR to UV, all right? So let's be very clear. Life will be very easy and the whole field of nonlinear photonics wouldn't exist, okay? So changing frequency is very hard. Wavelength is a spatial, parameter that comes from the interaction of the wave with the medium. Clear? So you can trap the light. So what you see here is actually a Maxwell solution to the space that I exposed here. And you can see here you have a solution nicely sitting inside silicon. That means the energy can be trapped inside this, right? When I say trapped inside this, in transverse it is trapped, okay? But longitudinally it is propagating. So this is actually a waveguide, right? It's fabricated, and if I put the light in, it is trapped in the XY plane here, right? Transverse, and longitudinally it is moving, all right? I can make this light go through these spirals, if I want, all right? So this is how a waveguide works, okay? This is very fundamental to photonic ICs. One should understand how the light is confined and it is moving forward. And again, photons can travel on its own because it's an electromagnetic wave, unlike electrons that requires potential to move. Electrons will not move unless I apply a potential. That's the energy that I have to spend. But for photons, I generate it, it just goes. Zero energy spent. Correct? Otherwise, I wouldn't be able to transport one photon for thousands of kilometers. Right? So that is the beauty of photon. The energy comes from the electromagnetic oscillation that pushes the photon forward. All right? Let's get into these two sections, right? One is photon source. I need to generate photons, and there are multiple ways of generating these photons, right? And I want it to be coupled to the waveguide, right? So if you want to generate photons, single photons, one way of doing this is quantum dots, right? So why quantum dots? Because you need to generate a single photon at a time. Bulk generators like the lasers and so on, that's a statistical process. You generate thousands and thousands of photons in a single shot, right? And then you have color centers. These are all defect sites from the materials that can also generate photons because of electronically available state for radiative transition. And then parametric down conversion, which is a nonlinear process, right? And also four-wave mixing, or rather wave mixing. You can mix two waves and create new energy, right? So which I will show you in the next slides, right? Both these quantum dots and these nonlinear processes. We are not going to talk about these things. They have their own advantages and disadvantages. This is for people who are more familiar with the area. So if I'm going to generate a photon, I want this to be deterministic. Okay, I'm going to do a computing. I want to have the photon now. Right? It's not like I'm going to do an operation now. I'll wait for the photon to come and then do my processing when I arrive. That's not going to happen. So it should be on demand. So that's very important that it is available, right? And the other things are more towards functionality and also integration advantages, right? So these are all the details for some of you who are interested. So let's look at this four-wave mixing, which is a very, very popular way of doing it for on-chip light generation, right? So what is four-wave mixing? So there are two waves that mixes and then generates two more waves, okay? So I have this two states, right? And then I can pump with a photon with an energy equal to or larger than the gap that I have, right? And then what happens is when the excited state going to radiate, right? Then they radiate two different photons. One is called idler and the other one is called signal, okay? So this is similar to some of the spectroscopy that you must have studied. So in the pump, again, it's a single pump frequency, okay? So the photon energy need to be, twice the energy that I'm going to put it. And then the idler and signal, it based on the, type of material that you are going to use here, right? It's a rather simple process, right? If I'm going to put a pump and then I can put a signal along with this, that becomes two waves, or there is no need for the signal, only pump is good enough, right? So these are two ways of doing it. So pump and signal is a classic way of doing for signal amplification, where the energy from the pump is transferred to the signal, okay? Coherently you can transfer it. But then that's not what we are looking at here, right? So we want to generate correlated photons from a single pump source. So I can remove the signal and then I can just pump it, find the right amount of energy that will generate idler and signal at the output end, all right? So this depends on a lot of material property, primarily nonlinear, term, that gamma that you see here. So the higher the gamma, the better the photon generation is, that I will show you in the next slide. And the next thing is the confinement. We discussed about, this energy need to be confined inside this waveguide, right? The higher the energy inside the waveguide, the better the generation rate is. And finally, the dependency on the power that you are going to give, okay? So you want this to be, pumped reasonably high, right? Large amount of photons need to be pumped. And then accordingly, how the energy is going to be distributed between this. 10 minutes, yes. So this is the process that I already mentioned. It can be pumped and then it will generate the signal and idler. And there are different material systems that can help you to generate this, right? So there is a school of material systems with different, chi3. This is the nonlinear coefficient that you are looking for, right? 10 to the power of 15, you can see here. Aluminum nitride is very good, lithium niobate, but silicon is not really good. But then what advantage that you get is this index. I told you that this index confines the light, the energy density is very high. So though I have a lower nonlinear factor, I can confine a large amount of power inside the waveguides that pushes the conversion efficiently larger. But there are some systems that are, for example, aluminum nitride, but then the index is only 2.1, 1 less than silicon. So there are multiple platforms that you can look at. This is an example of how this thing works. As I mentioned, you pump in the laser, right, a single laser, and then it will create two wavelengths that of our interest, right? So signal and idler, and then you can do the statistics on this. And what you see here is actually the spectrum of this. So this is the pump, which is suppressed, and these two are the new wavelengths that are generated. And the photons in these two wavelengths are heralded. That means they share the property, right? If I look at one photon on the right hand side, the other photon on the left hand side state, I know, because they are correlated or entangled. And you can see here the generation rate, or rather the coincident rate reduces. Coincident means generating the same photon at a given point of time. I just want single photon. If I reduce the power, the coincidence rate goes down. Okay, the generation rate also goes down, but the coincident rate goes down. What I mean by coincidence is you generate two photons at the given point of time, right? They are correlated, of course, but they are multiple of these pairs available. I don't want that. I just want one pair to be there, right? So if there are multiple pairs, then my confusion is which pair am I looking at, right? So one photon from this pair and the other photon, pair will be a confusion there, right? So I want that coincidence to go down, and you can see that happen. And you can use filters in order to remove all the issues that you have with the pump, right? So this is a very high Q factor with very high extinction to take out all the light out. Only in this particular frequency or wavelength regime I can take the light from the cavity. All right. So you can integrate all of this using just the waveguides. But what about quantum dots, right? You can also integrate quantum dots on waveguides. Okay. So this is a waveguide, and then if I put a quantum dot, right, I can simulate and show you that the quantum dot starts to emit much better than its emission in isolation. Okay, which you call Purcell effect. Okay, and this is something that we have experimentally shown, right? When you put a quantum dot on a waveguide, right, you can see here this small bump is what this emission from this quantum dot, right? And then you can show there is a reduction in the lifetime. That means the radiation is getting pulled, right, from this quantum emitter because of the waveguide that you have in the system. And this waveguide will extract the light from this quantum dots, and it can actually be taken out. So this is the excitation. You can see here the green light without the quantum dots, and here you see it becomes a little bit of yellow. It's because the quantum dots are getting excited and they are also emitting, and that emission is taken out at the output end of the circuit. So you can actually excite the quantum dots and also extract the light emitted from the quantum dots along the waveguide. So you can integrate light emission from these quantum dots. Okay. So the next thing is about manipulating these photons, right? So I talked about this phase and also the nonlinearity. This is something we have seen. How do we control this phase and why we want to control this phase? Okay. So the way that we do that is by something called interferometric device. Here, if I get the light in these two arms, by controlling the phase, right, I can say whether the light can go to the upper arm or the one at the bottom, right? Either through or to the cross by controlling the phase, right? So the phi and theta here helps me to control the phase, right? And this is actually a device, it's a poor picture, but you see the outline, right? So what you see there, and when you do that, you see here you can get a very good extinction where the light is in one end, it is going through. On the other, you can actually split it somewhere here, and then you can also have really large extension where most of the light will go into one of the arm, right? So this is how spatially you can control where the light will go. And why this is important? This is important to realize, certain mathematical functions, right? So you are coding your amplitude here, right? So I can code the amplitude and then I can code the path. So these two are very important in realizing large area or rather large scale computation like the one you see here. So this is a demonstration of such a process where a very complex matrix is being controlled using electronic circuits here, and this is basically a circuit implementation, right, on chip, right? And then you can also do boson sampling. This is again a very interesting experiment where you have the source part and this is the matrix part. In the matrix part, you see here all these network. This is basically done through interferometers, right? And if you have just 4 inputs, you're looking at 23,500 combination of outputs. As I told you, this is the power of quantum computing. I just need 4 input bits and I can define 23,500 combinations out of this, right? Already a massive improvement. And this is one of the demonstration from Xanadu, if I'm right? This is a 8-qubit quantum processor. It's not a integratable processor at this point of time. You see this whole rack, that's not the chip, this is the chip. This whole rack is the control electronics for the chip. So the control electronics, if comes on board, then you get much better understanding. Okay, I'll quickly run through this design of photonic devices, right? So what you see here on the top, those are all simulation. So this is also a simulation. And what you see at the bottom, those are all measured. These are all mapped fields, okay? So when you are designing anything, that functionality that you want, you can actually see those on chip. So for some of you who are doing, electromagnetic simulations, right? So those are all for real. So believe those color pictures because that's what you have on the wafer. Just 2 minutes, I will close it. And finally on the photo detectors, right? Primarily detecting the energy, all right? What do we want here? We want to measure the presence or absence of photon. That's all you want to do, all right? And also you want to count the number of photons, right? So that's what you are using it. So what is the specification for a photodetector? Operating wavelength, of course, how efficient it is, dark count. Right? I don't want to count when the photon is not there, right? These are all false shots. And maximum number of counts that I can get. This gives you the saturation, right? After a while, I won't be able to count, right? What is the maximum count that I can get? Operating temperature is a very important parameter, right? Do I operate at room temperature or cryo? Response time and also jitter, which are time-dependent properties that are important. Right? How do I do this? Right? Primarily, we measure responsivity. The challenge here is responsivity is basically current over power, right? It's current generated over incident power. But I'm not talking about power. This is not conventional photodetectors. I'm talking about single photon, right? And I'm fighting against the KT. The temperature and the black body radiation is already there. How do I measure single photon, right? So that is the challenge that I have, and the limitation here is to reduce the noise that I have in the system. And how are we doing it, right? So these are all the 3 popular ways of doing it. One is avalanche photodetectors that uses a single photon to, or a single photon to electron process, and then it amplifies internally so that I can measure the single photon event. Or superconducting nanowire based detectors, or transition edge sensors. These two are superconducting circuit based, okay? Operates at low temperature, noise is very good, right? Efficiency is beyond 80-85%. But the problem is this is all cryo operated, right? We are talking about millikelvin elements. So on this side you have room temperature operation, near room temperature, but noise and efficiency is a problem. But we can still operate this, and you can buy it off the shelf. This is Thorlab's catalog. You can buy, APDs right off the shelf. But superconducting nanowire-based detectors work the principle of generating some thermal effects on the superconductor. So when there is a superconductor, of course, zero resistance. There is no resistance. The moment photon hits the wire or the absorber here, it creates a hot spot, and the resistance locally goes up. Okay, and that is what you are measuring. So it breaks the superconducting nature there, and then it anneals back. Okay, because it is at cryo temperature. Because this is the whole rack that has this circuit, right, where the pumps and chillers are sitting there. But this block is where the detector is sitting. It needs to be at low temperature. But we want to put it on a chip, right? It's not a single standalone entity. People have shown that you take a waveguide and then you can integrate the nanowire here. So this is niobium nitride nanowire sitting on the waveguide. So this is something that you can do. And this is operated at low temperature, and you can see it can reach efficiencies over 80%, 80-85%. Okay, and you can see the dark counts are very, very low. You're talking about few photons is what you are counting as dark photons. And 2D material is another way of detecting it, which is very popular. This is work of Kaushik, where tungsten sulfide is a single layer monolayer that you have, along with few layer graphene top and bottom, and this can act as a single photon detector. An interesting thing is this can operate at room temperature, and this can be integrated with waveguide as well. Okay, so this is where our efforts are, and you can see here I'm counting 10 to 20 at the max, right? So I'm counting about 5, less than 5 photons. So that's the power of 2D materials as well that can be integrated. So this is the direction that we are taking. And in summary, what I have showed you is the potential of using photonic integrated circuits for realizing quantum photonic circuits. There is a proven record on various demonstrations. Now it's time to put them together and also improve upon this individual device performance, right? And silicon photonics is going to be a very important base for us, right? Because silicon photonics already exists, and we have a good platform, mature platform for doing that, right? And then, as I mentioned, for academics and also industry, there is quite a lot of scope to work on these functionalities that can be pushed for a room temperature quantum photonic circuit, not just for computing, but also for communication. And that slide is just to show that the level of integration that we are looking at, right? The number of components are just, blowing up as we move in time because of the complexity in the integration as well. With that, thank you very much. Sorry for taking 2 minutes more. I think I've ran over the Q&A time. I will leave it to you.
Thank you, Shankar sir. So if anyone has any questions, we'll just have a quick Q&A session, and we'll just give you mics. Please raise your hands.
Sir, good morning, sir.
You can sit.
Sir, in session you mentioned that complex problems, quantum computing is actually desirable. So if a problem is NP hard, okay, is it possible to solve those type of problems?
Yeah, it's primarily towards NP hard problems.
So is it possible to solve it in polynomial time using quantum?
That's the idea. That's the idea, right? So the boson sampling, right, is basically proving that point where the whole sampling was done. I forget, within few seconds. That would have taken about 600 million years for regular computing. So it's primarily driving towards NP hard problems.
Oh, thank you very much, sir.
Thank you, sir. So one basic question, I'm new to quantum computing and quantum. So what you said is source is always can be a quantum dot or a single photon generator. And the gates, my understanding is actually created using something similar to interferometer. Is
Correct,
that right?
Correct, that's correct.
So why we go for single photon and why not a light source?
Good question. So there are two ways to look at it, right? Why you call it as a quantum computer? Why not call it as, optical computer, right? So optical computing or quantum computing. The way that we define it is, if it is a optical computing, then you're talking about, the regular light sources, high power light sources. It can be microwatts. You're talking about, already millions of photons coming in. So there you're limited by the state that you can define. Again, it becomes either analog or digital. But then if I go to low photon counts, let's say few photons or even single photon, that gives me opportunity to not just measure the energy of the photon, but also polarization and phase of the photon, which I cannot do it when I'm getting 100 or 1000 photons, all right? So single photon becomes much more powerful in that sense. But then you can do this computing either discrete variable or continuous variable. There are two, ways of doing it. Where you use actually a single photon, okay? That's the ideal situation. But today we don't have, the source is the limiting factor, okay? So source is a limiting factor and also the losses that we have. But then if you look at, attenuated sources, that's what commercially viable option is, where you squeeze the phase to a very narrow distribution, okay? And then I can do computing on that. I don't need a single photon. I can still live with, a bunch of photons there, because I'm squeezing the phase so that I have confidence that this bunch of photons will have the same phase, right? So that certainty is there. So I can still operate with a laser, which is squeezed, right? Highly coherent, and then I can do computing on that. I don't need a single photon. Ideally, long-term single photon is what you want. Good, thank you very much. We'll stop.
So we'll end the Q&A session here. So if anybody has any other questions, you can mail sir or at IQTI office and we'll forward your queries. So once again, thank you so much, Professor Shankar, and we would like to present a small memento on behalf of IQTI office.
Okay. Thank you.